Chapter 8 of our book is entitled Drug Chemistry, and frankly that's false advertising. There's very little in this chapter that's actually about drugs until the very tail end of the chapter. What it is about is organic chemistry, and frankly you can't understand the chemistry of drugs unless you know a little bit about organic chemistry. So we'll run through the chapter, we'll define what organic chemistry is, we'll frame it in its simplest sense in terms of Lewis structures and shape. And the rules for organic chemistry are quite strict and very simple, so that's a big help. And we'll look at some hydrocarbons first, and then we'll look at how hydrocarbons with the same formula are allowed to have different shape. Those are called isomers. And then we'll look at something that we've already seen, that the three-dimensional shape of a molecule can affect its polarity. And in biochemistry, shape is incredibly important. And then we'll look at some functional groups. Those are parts of a molecule that contain oxygen and nitrogen, and that's where the reactions in the molecule actually occur. And then we'll go and pull up some structures of some drugs and point and see what we can recognize. There's no better place to start than with the periodic table. So let's look at where carbon is in the periodic table, because organic chemistry is the covalent chemistry of carbon. Remember that covalent chemistry is when atoms decide to share electrons between each other until each of the atoms has a filled shell, or 8 electrons. Some people call that the octet rule. So there's carbon, and carbon is in group 4 on the periodic table. It's in group 4, which means it has 4 valence electrons, here represented as a Lewis structure, with the atom in the middle, and then 4 dots, each representing an electron. And you need 2 electrons shared between 2 atoms to make a covalent bond. So if carbon has 4 atoms unpaired that it can share, that means that carbon always makes 4 bonds. This is a very convenient and very strict rule for us, that in all of the complexity of everything that we're about to see, carbon will always have 4 bonds. 4 single bonds around a central carbon is a tetrahedron. And a tetrahedral geometry has a central atom, and when the bonds are drawn with the line in the plane of the paper, that means that's the flat part. But if a bond is wedged, it means it's coming out towards you. And if a bond is a hatched line, it means it's going away from you. So this is a 3-dimensional shape. 2 of the bonds are flat to the paper. One of the bonds is pointing out towards you, and one of the bonds is pointing away. So let's revisit some of the rules for Lewis structures, how to combine atoms together. A covalent bond is 2 electrons shared between 2 atoms. If this is an atom, and that is an atom, and this has an electron, and that has an electron, then I've just made a covalent bond between those 2 atoms if I have shared those 2 electrons between those 2 atoms. Each and every atom wants to have 8 valence electrons. 8 is a magic number in chemistry. We have 8 groups on the periodic table, and the atoms in group 8, helium, neon, argon, krypton, xenon, they're inert. They don't react. So there's a magical, just special situation when you have 8 valence electrons. Then your atom becomes unreactive. It ceases to want to react. So each and every atom is going to want to have 8 shared electrons. Now that cannot happen for hydrogen, because hydrogen is in period number 1, and there are only 2 atoms in period number 1. There's a hydrogen and a helium. And so hydrogen only needs two electrons. If you've stuck all of the atoms together and you're in a situation where not all of your atoms currently have 8 valence electrons, then just keep bonding. The answer is in there somewhere. Just keep plugging away. And then this turns out to be incredibly helpful for us. Because hydrogen is in group 1, it has 1 electron, which means it can only make 1 bond. And because chlorine and bromine are in group 7, they're 1 electron from having 8 electrons. So hydrogen and chlorine and bromine only ever make 1 bond, exclusively. Oxygen and sulfur are both in group 6. 6 is 2 steps away from 8, which means they always make 2 bonds. Nitrogen and phosphorus are in group 5, which means we always see them make 3 bonds without exception. And carbon. Carbon is in group 4. It has 4 unpaired electrons and will always make 4 bonds. With this, we can reproduce on paper most of biochemistry. Biochemistry is made up of carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and then just a sprinkling of other atoms. There's a little bit of magnesium in there, there's a little bit of iron in there, a little bit of zinc, but it's mostly these. That's what biochemistry is. And because our drugs act upon biochemical receptors, the 20th century concept of what a drug is was a mimic of the shape of something that we can generate from these atoms. So let's start by looking at the Lewis structures of some simple organic molecules and then work our way out and make them a little bit more complicated. We'll start by looking at the hydrocarbons. Hydrocarbons are molecules that contain only carbon and hydrogen. Okay, so carbon, group 4, always makes 4 bonds. Hydrogen, group 1, always makes 1 bond. Our simplest hydrocarbon is methane. It's a component of natural gas and it has chemical formula CH4. So if we drew the Lewis dot structures of just the atoms, we would see that carbon has 4 unpaired electrons and that the 4 hydrogens each have 1 unpaired electron, and I need 2 electrons shared between 2 atoms in order to make a covalent bond. Then when the hydrogen attaches to the carbon and it shares its electrons, I can make a covalent bond right here. 2 electrons shared between 2 atoms. This is the Lewis structure for methane. And if you look, that central carbon is in shared possession of 8 electrons, and each of the hydrogens has 2. This is a Lewis structure. Now, Lewis structures strictly are supposed to show the dots. If they don't show the dots, then technically they're not Lewis structures. Technically, if I give you another simplified representation of a covalent bond, just being a line, the line represents a bond between 2 atoms, then it ceases to be a Lewis structure and starts to be a Kekulé structure. Our book and all the online resources that come with it don't do a good job at that. So when it says show me a Lewis structure, or this is a Lewis structure representing something, and it shows you the lines, it's technically not true, but it doesn't matter. Methane, our simplest hydrocarbon, belongs to a family called alkanes. Now, alkanes contain only carbons and hydrogens, they're hydrocarbons, but beyond that, they contain only single bonds. So this is as simple as it gets. This is part of the family of alkanes. Methane is CH4, and here is its structure. Ethane is C2H6, and here is its structure. Now methane was a tetrahedral carbon surrounded by hydrogen, and what we've got here is that in ethane I've got two tetrahedral carbons stuck together, and then the hydrogens go on the outside. The hydrogens are never going to be between bonds because hydrogen can only ever make one bond at a time. It is always on the outside. It can never be between two other atoms. Propane is C3H8, butane is C4H10. Here's butane, 4 tetrahedral carbons bonded together in a chain. Carbon, better than any other atom on the periodic table, sticks to itself. Each of those carbons is 4 single bonds. And then pentane would be C5H12, hexane would be C6H14, heptane would be C7H16, and octane, which you might recognize from gasoline, is C8H18. So, there's a couple of things here on this list that they have in common. They all end in ane. We're going to have the root of a word, we're going to have a prefix that goes here, and then ane tells us this is a hydrocarbon that contains only single bonds. And the prefix that goes here tells us the number of carbons. Meth is 1, eth is 2, prop is 3, but is 4, pent you might recognize as being 5, hex you might recognize as being 6, hept and oct. And those prefixes are going to be consistent amongst all chemical naming systems. So we're going to, once we know it once, we can use it for everything else. Okay. Now, if we take a close look, here's butane. Every carbon in the chain holds on to 2 hydrogens, and then there are 2 at the end. So generically, we could say that for every number of carbons that we have, n being just a number, an integer 1, 2, 3, 4, 5, 6, 7, that the number of hydrogens that belong to that carbons is twice as many, and then 2 at the end. So when I have 5 carbons, I will double that to be 10 and then add 2 so that the chemical formula for pentane comes out to be C5H12. Okay? This is the generic formula for alkanes. So we've just seen that the chemical formula C4H10 represents butane. But meaning 4 carbons in a chain. C4H10 represents butane, and what if I took this end carbon off and moved it to a new place? And the rules for organic chemistry are very, very simple and really quite strict, is that carbon has to always have 4 bonds, and hydrogen can only ever have 1 bond. This is C4H10. That is also C4H10. This has a longest chain that is 4 carbons long, and so is called butane, because meth, eth, prop, but. This longest chain is 3 carbons long, and when we teach the organic chemistry to the chemistry majors, we teach them stop reading left to right because your longest chain might actually go around a corner. You have to look at this from all directions. The longest chain in this molecule is only 3 carbons long. So this is a propane of some description, and it's an ane because there are only single bonds. And then I have something. If I were to number those carbons, 1, 2, and 3, because they're in a chain, at carbon 2, there is one carbon, meth, hanging off of it. So this is what we would call a substituent, or a side group, or a side chain, and it is dangling off the longest chain at the 2 position. So the rule for naming is find the longest chain. The longest chain is 4 carbons in a row. Identify, do you have only single bonds? Yes. So this is butane. Find the longest chain. There are 3 carbons. Does it have only single bonds? Yeah. So this is a propane, but it has a meth, 1 carbon, attached at the 2 position. So it is a methyl. The YL here tells us that's little adjective, that this is a side group. This is methyl propane. These are called isomers. Isomers have the same chemical formula, but different shapes. And you may have heard me once already today say that in biochemistry, shape is absolutely everything. You're going to have a receptor that is a particular shape, and then you're going to have something fit inside that shape in order to send a signal. In biochemistry, these two might have different function. Same chemical formula, different shape. These are isomers. Let's look at another class of hydrocarbons. The alkanes that we just saw contained only single bonds. They belong to a classification called saturated hydrocarbons. Saturation is going to mean that hydrogen is in all of the available places and contains only single bonds. Unsaturated hydrocarbons are going to be missing some hydrogen. Alkenes have the general formula CnH2n. So for every number of carbons, we're going to double the number of hydrogens. Now remember, for alkanes, we tagged a 2 at the end of that because there was a hydrogen on either end of the chain. Well, alkenes contain a double bond, a carbon-carbon double bond. They all end in -ene, and they're going to have a prefix that goes here, and that prefix follows the rule that we've already seen. Now, our simplest alkene has to have a carbon double bond between 2 carbons, so there is no such thing as methene, because that would only be 1 carbon. So our simplest one is ethene. If we look, this carbon has 1, 2, 3, 4 bonds. This carbon has 1, 2, 3, 4 bonds. So the carbons each have 4 bonds. The hydrogens each have 4 bonds. This is C2H4, 2 carbons, ethene. Propene would have the carbon-carbon double bond right here. This carbon has 4 bonds. That carbon has 4 bonds. And then I have a tetrahedral carbon right here, like an alkyl, belonging to an alkane, like an alkyl group. that it has 4 single bonds. So these are different. These, if you remember back to when we looked at shape and VS EPR, these are trigonal planar. They're flat and triangle shaped or Y shaped. And then these ones are tetrahedral. The fact that some of our molecules are now going to be flat and others have 3-dimensional shape, and that this is rigid, whereas this is allowed to rotate, that has a big impact on the 3-dimensional shape. If we count 1, 2, 3 carbons, and then 1, 2, 3, 4, 5, 6 hydrogens, we see that the number of hydrogens is twice as large as the number of carbons. That fits my general formula here, alkenes. Okay, one last one. This is butene. 4 carbons, 1, 2, 3, 4. Each of the carbons has 4 bonds. That one has 4 bonds, this one has 4 bonds, that one has 4 bonds. So this is C4H8. But we're not quite done, because if you wanted to buy some butene, some C4H8, and you went to the website to buy some, you would find that there are 2 versions of butene. That there is this one, and then there is the one where the double bond is in the middle. One, two, three, 4. 4 carbons, so it's a but. There's a double bond, so it's an ene. And 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. These are both called butene. They're both alkenes. They're isomers. And so we have to think of a way of telling them apart. If we go ahead and number the carbons in the chain, we see that here the double bond starts at carbon number 1. This is going to be called 1-butene, and here the double bond doesn't start until carbon number 2. So this isomer is called 2-butene, and this isomer is called 1-butene. In organic chemistry, the rules are very simple, the rules are very strict, but the number of permutations can get a little bit bewildering. We're only looking at small molecules. When we think about a protein, and a protein might have 250,000 atoms in it, we have to think about exactly what the shape of what's important is. Okay, let's look at the last 2 forms of hydrocarbon that we need to know about. Alkynes. Alkynes contain a carbon-to-carbon triple bond. One of the very first things that we said about Lewis structures was stick the atoms together, and if you've stuck all the atoms together and you still haven't had 8 electrons on each of the atoms, just keep bonding. Just make them bond to each other until they have 8 electrons, which means this carbon has 4 hydrogens. I'll write it out the full way because we haven't quite seen that yet. There you go. That carbon has 4 bonds. This carbon has 1 to the left and 3 to the right. This carbon has 3 to the left and 1 to the right. And each of the hydrogens has just the 1 bond. This is prop for 3 carbons. Ine because I contain a carbon-carbon triple bond. They have generic formula CnH2n minus 2. Double the number of carbons and then subtract 2 from it. And then there are cycloalkanes. Cycloalkanes are just alkanes, but the ends have linked up with each other. Carbon loves to bond to itself, and in this sense, we've just closed the loop. So, in a cycloalkane, every carbon has 4 bonds, and every carbon is holding on to 2 hydrogens. So our chemical formula here is CnH2n. Just double the number of hydrogens that you have for the number of carbons. Okay, this structure, this is a Kekulé structure. This is what everyone calls a Lewis structure, even though it's not. This is a condensed structure. And in a condensed formula, you write the atom labels and you write the number of hydrogens that are attached. And then we have the line structure. And in a line structure, we don't put any atom labels in at all, not for carbons and hydrogens. At the apex right here, there's a carbon. And we leave hydrogens off because we just assume that if you've got carbons, then there are hydrogens. So we don't even bother labeling them. To start with, this is probably not what we would recommend, but when the molecules start to get larger and you have to write them down lots and lots of times, people just automatically slip into this form of notation. All the molecules that we've seen up to this point were all hydrocarbons, and they're all non-polar. None of them had an electronegative atom inside. And if you don't have an electronegative atom, then you cannot have a polar bond. And if you don't have a polar bond, then you cannot have a net dipole and be polar. And in the world of oil and water don't mix and like dissolves like, we're going to need some polar organic molecules that will be soluble in water, that will be soluble in the aqueous biochemistry system rather than in the non-aqueous fat soluble system. Okay, so all hydrocarbons are non-polar. Let's go ahead and throw in some of these electronegative atoms and see what we can make. Okay, let's look at chloroalkanes as our first polar molecule. I'm going to pick this first because it's probably the simplest. Chlorine, group 7, can only make 1 bond. So what we can do with the chlorine is replace a hydrogen. So wherever there was a hydrogen in any of your previous molecules, you can go in and just switch it out. So this 4 bonded carbon, 4 bonded carbon. Carbon has 4 bonds. Each of the hydrogens have 1 bond. And then I've got a chlorine in the position that we'd previously seen a hydrogen, because chlorine always makes 1 bond, hydrogen always makes 1 bond. This is the Kekulé structure, or what our book's going to want to call a Lewis structure. Here is its condensed formula, CH3, CH2, Cl, and this would be chloroethane. 2 carbons, eth, only single bonds, ane, and then replace a hydrogen for a chlorine, and it becomes, ethane becomes chloroethane. If this is a chlorine in a position where there used to be a hydrogen, then my 3 carbons in a chain were a propane. This becomes chloropropane. This is the Lewis structure, really a Kekulé structure. Here's the condensed formula, Cl, CH2, CH2, CH3. Okay? That would be chloropropane. But if you wanted to buy chloropropane and you went to the manufacturer's website and you tried to buy chloropropane, you would find out that there's more than one type of chloropropane. Because who's to say that the chlorine had to be in the position that you first drew it? So this is also chloropropane, but they're different from one another. Same chemical formula, different shape. If that's carbon number 1 and carbon number 2 and carbon number 3, and that's carbon number 1 and carbon number 2 and carbon number 3, we could call this one 1-chloropropane, and we could call this one 2-chloropropane. They're isomers. Let's look at organic molecules that contain oxygen. Now this is a tiny bit more complicated because oxygen makes 2 bonds. So oxygen's going to oftentimes be between 2 other atoms. It's going to have a bond to the left and a bond to the right. But I think that the simplest place to start would be to look at alcohols. This is ethanol. Ethanol is the alcohol that we control and tax because humans consume it. It has 2 carbons in a chain, eth. It contains only single bonds, so there's the an part right here, and then it contains this group, carbon, oxygen, hydrogen. And when you have a carbon to oxygen to hydrogen set of bonds, that's an alcohol. So this is ethanol. It has a chemical formula of C2H6O. If we looked at propanol, using the same logic that we just did for the chloroalkanes, we can see that there are going to be 2 isomers. There's going to be a situation where we can have the carbon, oxygen, hydrogen alcohol group be at the end of the chain, and having it at the end of the chain is the same as having it at the beginning of the chain. Okay, you don't have to number these things 1, 2, 3 from right to left the way that we read in the West. No, it's the molecule's been written that way. You have to interpret it. So that gets to be carbon number 1, and that's number 2, and that's number 3. And then we've got a situation where it's in the middle. So there are 2 isomers, one where the alcohol is at the end and one where the alcohol is in the middle. 1 propanol and 2 propanol. Okay, if we cast our minds back to the chapter where we looked at shape and polarity, all these carbons are tetrahedral. The oxygens have lone pairs of electrons and 2 bonds. So the oxygens are bent in geometry and they are polar. They're going to be pulling electrons towards themselves, away from the hydrogen and away from the carbon. The oxygen is electronegative. That means I have a polar set of bonds. I've induced a net dipole into the molecule. Like dissolves like. Alcohols dissolve in water. Alcohols dissolve in water because they're polar. Our hydrocarbons, completely non-polar, don't dissolve in water. In fact, they don't even mix with water. They form 2 layers. Okay? So just by adding an oxygen in here, I've completely changed the physical behavior of the liquid that I've generated. That an alcohol behaves fundamentally differently than a hydrocarbon does. Now, that's alcohols. But there's something else lurking here. This is a very small molecule. This is ethanol, and it has a carbon to oxygen to hydrogen set of bonds. But it is not the only representation that C2H6O can make. If you think hard enough, you might be able to imagine this molecule. It's C2H6O, but it's not an alcohol. It's not an alcohol because it doesn't have the carbon, oxygen, hydrogen set of bonds. And again, if we go back just a chapter or two, we've mentioned that if there is a hydrogen directly attached to an electronegative atom, that the intermolecular attraction is called a hydrogen bond. So these are highly soluble in water. I've made that hydrogen bonding ability go away. This is protic, makes a hydrogen bond. This is aprotic, doesn't. This is polar, because at the end I've got a very highly electronegative atom next to something that is way over on the other side of the periodic table. Now I've got it sandwiched between two carbons. So this one is mostly, it's got a little bit of polarity, but this one is mostly non-polar. And whereas that is an alcohol, this is an ether. Ethers contain carbon, oxygen, carbon sets of bonds. So if you see carbon, oxygen, carbon, it's an ether. If you see carbon, oxygen, hydrogen, it's an alcohol. These are going to be two very common isomers of each other. Okay, let's look at some more complicated molecules. These all share something in common. They all have a carbonyl carbon, carbon to oxygen double bond. They all have that. And then they also have a bond to another electronegative atom. Okay. Carboxylic acids. This one is ethanoic acid. Count the longest chain. There are two carbons, meth, eth. And it is carboxylic acid, so it ends in anoic acid. All I have here is a prefix and a suffix. That you count the number of carbons, and then they all end in anoic acid. 3 carbons would be propanoic acid, 4 carbons would be butanoic acid. That's the name. Carboxylic acids are very important biologically. These are one of the building blocks of fat and also of protein. Esters. Esters are just like carboxylic acids, except instead of having a carbon-oxygen-hydrogen bond set, look, this is an alcohol. So carboxylic acids are carbonyl alcohols. It has a carbonyl carbon-oxygen-carbon bonding set. So this is kind of like an ether right here. These two are cousins of one another. Esters, biologically relevant. You will find them all over biology. Anytime that you have a smell from something biological that is even remotely pleasant, probably an ester. It's responsible for all of the spicy and minty and fruity smells that come out of nature. And then we have amides. Oh, so this one right here, go back to the ester for just a second. The longest chain is 1, 2, 3. So the root of the word is propanoic acid. And then I'm going to throw a methyl on the front of it. So this is the methyl substituent of propanoic acid. It becomes methyl propanoate. Amides, same thing, a chain, a carbonyl, a bond to an electronegative atom. And sometimes the amides have a hydrogen here and sometimes they have a carbon. It depends. These are the building blocks of proteins. If we take an amine, which I'll do in just a second, and a carboxylic acid, and you cross-link them to one another, you bond them to one another, then you make amides. And amides are what keeps the building blocks of proteins together. The building blocks of proteins are called amino acids, and you build them into amides. This one would be called ethyl butyl amide. There's the ethyl, it's a substituent, and butylamide is the name of the longest chain. Okay, so let's look at organic molecules that contain nitrogen. We've seen what alcohols look like. Alcohols contain oxygen. Oxygen is in group 6, so it always makes 2 bonds. Well, nitrogen is in group 5, so it always makes 3. If we were to replace the alcohol's oxygen with a nitrogen, we make the amine. It just has 2 hydrogens attached. So this is 1, 2, meth, eth, amine. This is ethylamine. There's a very important biological molecule or class of molecules called amino acids. And they all look like this. They have an amine, that's a single bonded nitrogen at this end. And then they have a carbon in the middle. And that carbon is tetrahedral. It has 4 bonds. One of them is a hydrogen. And the other one is something else. And there are about 20 naturally occurring amino acids. If you put a hydrogen here, you make glycine. If you put a methyl here, you make alanine. They all have their own unique names. There's about 20 of them that are biologically active. And then at the end, we have a carboxylic acid, a carbonyl alcohol. Well, it turns out that this end of the molecule, because it contains a lone pair of electrons on a nitrogen, is basic. And this end of the molecule, because it contains a hydrogen directly attached to an electronegative atom, is acidic. And when you put acids and bases together in solution, you lose water, and the base grabs the acid, and you convert the acid end of a carboxylic acid and the amine end of another carboxylic acid into this amide. And that amide is called a peptide link, and what you've just done is you've built a protein that we assemble multiple amino acids and we polymerize them together. We make them be a long chain, and that chain becomes a protein. And biologically, we have mechanisms that allow us to select what this side chain is going to be. And the side chain decides whether it's going to be a long, straight type of protein, or if it's going to start wrapping around and being globular on itself. Okay? So those are the building blocks of organic chemistry. The only thing that's left in the chapter is a little bit about a solvent extraction. I'm going to do a solvent extraction as this week's virtual lab exercise. And then there is a quite useful table at the end of the chapter about, here are some drugs, let's look at what their shapes are and what they can tell us about that. And that's what we'll do next. Okay, one more thing. We've got to look at some acidity, basicity, and how it relates to solubility. In a previous chapter, we learned that all sodium salts are soluble in water. And we also learned that all ammonium salts are soluble in water. Okay, how can we take the information in this chapter and use that solubility information that we already have and link the two? If we look at carboxylic acids, this is the shape of a carboxylic acid. Hydrogen is in group 1. Sodium is also in group 1. This hydrogen is covalent, but I can easily replace group 1 for group 1 and make this become ionic. Now I have the sodium salt of an ionic conjugate base of a carboxylic acid. I've made sodium acetate out of acetic acid. Ethanoic acid or acetic acid, commonly known vinegar. I've made the sodium salt of it. It's guaranteed to be soluble in water. I had no guarantee that this carboxylic acid would be soluble in water. And when you make them big here, you put lots of hydrocarbon here, then they're not soluble in water. So some of the big carboxylic acids, not soluble in water at all, very low solubility. But when you react them with base, you guarantee that they're going to be soluble. And then we can manipulate things, move them around in solution, and when we want this back, I just add acid to make the base go away, and I get that back. Okay? Conversely, with the amine, amines are bases because they have a lone pair of electrons that they can give away. Our definitions of acids and bases. An acid is anything that puts H plus into solution. A base, anything that takes H plus away. The Lewis definition of a base is an electron pair donor. Well, there's the electron pair right there. So this is a base, and it's going to react with an acid. It's going to make a salt. And the amine is going to become an ammonium. Positive charge on a nitrogen is an ammonium. It's guaranteed to be soluble in water because all ammonium salts are soluble in water. We'd said that earlier. Okay? So this is a strategy that people who want to make new things or investigate what we have, it's easy to separate these two. If these were in a mixture of one another, and we added base, all the carboxylic acid would go into solution and all the amine would stay behind. If we had a mixture of these two and we added acid, all the amine would go into aqueous solution and all the carboxylic acid would be left behind. This is a table from the book that shows functional groups, what they look like, how to recognize them, and gives an example of a molecule in which those functional groups appears. Let's go look at some drug structures and see if we can identify what functional group is present in those drugs and what that means. This is a comparison of cocaine versus crack. Okay, so we know just from watching Hollywood movies that cocaine is a white powder that's finely divided and that crack is hard little granules. When we look at the structure, we see several things. First of all, I'm going to pick the pen. This group. We didn't talk about that, but that is an aromatic group, a 6-membered ring, so like a cyclohexane, but then alternating double bonds, 3 of them that go around the ring. This is a phenyl or aromatic ring, and it's quite common in nature, and that's the same in both. Attached to that is this group, which is a carboxylic acid residue. it has the carbonyl, and then an ether, and then a carbon. So this is an ester. In fact, cocaine contains 2 esters because that's an ester, and this is an ester. This group that goes carbonyl, oxygen, carbon, that's an ester group. Okay. So these 2 structures are just the same as each other, but with one difference. In crack, that nitrogen is basic. It has a lone pair of electrons, whereas in cocaine, it has been acidified, which means this one is an ammonium salt. This one, powder cocaine, is guaranteed to be soluble in water. And we know this from studies, because when the drug police raid people's houses, they oftentimes will flush the cocaine down the lavatory. And in cities like Venice, where you actually live on top of the water 100% of the time, they have measured the amount of cocaine that is dissolved in the rivers and canals in Venice, and it is significantly higher than it should be, because cocaine is water soluble. It finds its way into the water supply. This is table 8.6 from our textbook, and it shows the structures of some illegal drugs and also of some prescription drugs. Let's see what we can find. First up, methamphetamine. Meth, we've just learned, means 1 carbon. So the methamphetamine is going to refer to that methyl attached to this amine. Also present in this molecule is an aromatic ring, 6-carbon ring with 3 double bonds. This molecule, basic, not soluble in water until you were to acidify it. Got a lone pair of electrons on that nitrogen. It's going to make it basic. Cocaine we've seen. Heroin. Heroin looks a little bit more complicated. Let's see what we can see. Over here, that group right there, that's an ester. There is also an ester here. In the middle, there's an ether, carbon, oxygen, carbon, bridge, right there, that's an ether. This is an amine, a nitrogen attached to a carbon is an amine. Also in heroin, we have an alkene, it's carbon-carbon double bond right there. And then we have this set of 3 carbon-carbon double bonds, all equally spaced in a 6-membered ring. That's an aromatic group. Taking a look at THC, the active ingredient in marijuana, we see that there is an alkene, there is an ether, there is an aromatic ring, There's a long chain of carbons. So in all likelihood, this molecule, everything that we've circled up to this point, all of that is non-polar, not soluble in water. And then there's a little polar group right there, just the one. That's an alcohol. Drugs that are soluble in water, they become part of our water-soluble metabolism. The water-soluble metabolism in the human body can be flushed quite rapidly. So it's much easier to pass a drug test where they're testing for water-soluble drugs like cocaine. It's much more difficult to pass a drug test where they're looking for the fat-soluble, the non-polar drugs, because they linger in your body's fat-soluble system much longer times than the water-soluble ones do. Let's skip to the bottom of the table and look at prescription drugs that have been designed for one particular purpose. Most of these are for killing pain, dulling the nerve impulse of pain, or dulling the nerve impulse associated with anxiety. And these are commonly abused by the general public. Okay, there's a couple of things that each of these have in common. There are lots of six-membered rings. Biology loves six-membered rings. It's also kind of fond of five-membered rings as well. So if we take a look at this first, we see there's a hexagon here and a hexagon there and a hexagon here. Six-membered rings. And then they're held together by a five-membered ring, by a pentagon. It is very common in biology to see five-membered rings and six-membered rings. The six-membered ring on the left has three double bonds. It's aromatic. That makes that six-membered ring be flat. The others all have some three-dimensional shape. And then let's see what else we've got in here. This group right there, a carbon, oxygen, carbon set of bonds, that's an ether. There is also an ether here, carbon, oxygen, carbon. And then we have a ketone, a carbon, oxygen double bond with carbons on either side of it. That's a ketone. Up at the top, there is an amine. Biological molecules are often going to be found containing biological nitrogen. These very weak bases are biologically active, and there's an entire class of chemistry that belongs to them. And lots of them are psychoactive. They all have some kind of neurological response. Okay? So take a look through the list and see if there's anything in there. There's a couple of things on this list that we haven't explicitly seen. In psilocybin, there's a phosphate. We hadn't talked about that. You're not going to see an awful lot of that. But you're going to see repeating six-membered rings, five-membered rings, and nitrogens.